Hello students, welcome everyone into this lecture. Today we'll be discussing about column design. Last class we have discussed about BNBC design of the building. The plan you are just using will be similar to this one. So plan of the building, from there you can see there will be some columns. So basically three types of columns will be there. So these columns, we call this the corner columns. There will be another type of column. This type we call this the edge columns, and there will be another type of column which we will be calling as the mid columns. So the edge columns, corner columns, and the middle columns, all these types of columns we'll have to design. So if design, you know that by this time I think you have learned about all the basic methods, the calculations formula, which we'll be discussing for the particular drawing for a plan view. So in an integrated view today we'll be discussing how to analyze these things in a column. So first of all, to start with, we will be saying that you have the diagrams, all the diagrams drawn by this time for all the frames. In this case we will have 8 2D frames, so from all the frames you have drawn the diagrams, bending moment diagrams, shear force diagrams, axial force diagrams, and this is a typical frame, 2D frame you will be getting based on your story number of the building. And then if we draw, the column is all about the, the column is all about the axial force in particular. But beyond that, we will have also the moments of the columns which will be required for us. So for this we will have basically the axial force diagram, which will be like, say for example this one. This will be a typical axial force diagram, which will be and all this will be negative value of the column. Axial force will be negative in case of column, just because it will be acting on towards the gravity direction, as you know. So from axial force, all these diagrams will be similar for all these columns. So from story to story, as we go below, and at the very lowest portion of the column, this portion we will get the maximum axial force. So from all the columns, as we all know, the pattern of the columns, the loading pattern is well known to us. So what we'll do, we will be, say we denote these columns as C1, C2, C3, C4, like this, C5, blah blah blah. So all the columns, if this is the C1 column, then we have the axial force diagram for this one. Okay. So you will be creating a table again, as we have created for the beams. So column 1, column 2, column 3, like this one. And in this portion we will be adding up the axial force. And axial force, it will be the maximum axial force actually. The maximum axial force we'll be using here, say for example this is 100, this is 120, this is 150, this is 225. So then the maximum amount will be adding up here 225 kips. So in this method we will be using all the axial forces here. And remember one thing, that this C1 column you will be getting the similar value of this one from the axial force diagram of this frame, this particular frame. So say for example, if we say this one is A and this one is 1, then if you draw the this frame number 1, then you will be getting this C1, and also if you draw this A frame, then also you will be getting the C1, and the similar value you will be obtaining from these two frames as well. It is possibly the similar value. So if not, in any case, if not, obviously it will be, but if it is not, then what we'll be doing, you will be obviously adding up the maximum value of from the both of these two frames, including this into here. Okay, so after that, all the values you'll be writing up here like this. The maximum values will be adding up in this chart, and finally what we'll be doing that we will be finding out the maximum values. We'll be getting the maximum values as well. But before taking the maximum value, we need to draw also the bending moments. We'll have to also sort out the bending moments as well. So in this case, you will be getting two types of moments. One is moment at x direction and moment as y directions. So from the very beginning, you will have to sort out which is the x-axis and which one is the y-axis. So if you have sorted out this thing, then what is mx and what is my? You need to find out this thing first. Say for example, if I draw a column, typical column like this one, then we'll have axis. We'll have axis in like this. So this is x-axis and this is y-axis, and in that case, a moment which will be the moment which will be acting with respect to x-axis. So with respect to x-axis, the moment is working in this direction, so which is trying to make this portion over that portion. So it tries to bend this surface with respect to x on that surface, and that moment that we are denoting as mx. We say this one is mx, and for our convenience, which method we'll be using, we can say this is m1x. Okay, and the moment which is trying to bend this particular surface over this one, or vice versa, whatever it is, the moment which is acting with respect to this y-axis, and say for example this is working in this direction, and that we will be denoting as m2y. So let's use different colors to make it more comprehensive. This is m2y. So with respect to y, this moment is acting in this x direction with respect to y, that is m1y. We can denote it as m1y actually, m1y. Okay, so this is mx and my we need to understand, and this m1x and m1y we need to find out from our bending moment diagrams of the columns. So by this time you might have drawn the diagrams for all the combinations, or all of the combinations. If you have drawn the bending moment diagrams, you need to sort out the bending moment diagrams of the you need to draw the bending you need to sort out the bending moment diagram combination and the maximum values of mx and my. So from which diagram you will be getting the bending moment diagram of x, and which one will give you that my. That is our main concern here. So if you are drawing this frame number 1, if this is the frame number 1, then you will be getting, if we draw the bending moment diagram, say for example this type of bending moment diagrams will be getting, say for example you might be getting a bending moment diagram like this one might be a bending moment diagram pattern, this one like this one. Okay, so if this is the pattern on bending moment diagram, you will be taking this the maximum bending moment diagram within this column, say it will be in this portion or in that portion, whatever it is, whichever the portion within the C1 column, you will be getting the maximum moment amount. If we are drawing the one frame, then obviously we are drawing the diagram when the wind load or the lateral load is acting upon this plan view, as you can see from this direction. So if the force or lateral force is acting parallel to the x-axis in this direction, then the bending will be occurring within this C column. That will be called the M1y. So the moment value you'll be obtaining from this will be M1y. And similarly, if you draw the A frame, in A frame the bending moment diagram, if you draw for C1 column, you will be getting the column bending moment for the lateral load in this direction, either in this direction or that direction. For each direction you will be drawing this, if not the symmetric view of this building, if not the symmetric, then for all four directions you will be getting the values and the maximum values, whichever direction, whatever the direction which is governing, that value you will be taking in account. So for example, said if this direction gives you the maximum value of bending moment for C1, then you will be taking that value. Otherwise, if this direction lateral force will give you the maximum value for C1, you will be taking this direction. For from this one and this one, the maximum value that will be taken, which will be giving you the maximum mx. And in other cases, if you see, I have said for about this direction lateral force, so obviously there will be lateral forces in this direction as well. So if you see in either of this direction, whichever will give you the greater bending moment. So obviously for this directional lateral force you will be obtaining one maximum bending moments, and for this directional lateral force you will be obtaining another bending moment diagram, and from there you will be getting another maximum amount of bending moment. So from this one and that one, the maximum bending moment whichever you will be getting for C1, that will be denoted as my, and the maximum moment you will be getting from both this one and this one, two diagrams, you will be sorting out the maximum moment amount, that will be, you will be getting that as mx. So these two values is very much important for us. For C1 you will be writing there as the maximum moment, that will be from, if my, you will be writing m1x and m1y, both of these two you will be writing upon here. So for example, if you get m1x as 25 for example, and m1y say for example 55 cubic feet, you have obtained, say for example. Okay, so in this case all of the columns like this, you will be drawing the similar pattern, follow the similar pattern, and sort out all of the moments here as well. Say 65 dot blah blah blah. Okay, then after this, what is your task? Our task is to design all of the columns. So if you ask, okay, why can't we take the maximum value? Let's go for the maximum axial force and design the similar column or all the columns similarly. But no, in these cases there is a problem for this, just because although the axial force might be greater in amount, but the moment might vary, and therefore the design of column might not be governing the maximum axial force all of the time. That's why you will have to design or satisfy your column section for all of the columns. Okay, we'll be giving example now how to proceed. We will be following, there were two methods as I can remember for eccentric columns. So we cannot design this column as accordingly the concentric column as we have earlier learned about this in theoretical courses. In addition to that, there are some eccentricities, as there are moments, as you can see. So as there are moments, obviously there will be eccentricities acting upon there, and the axial force is not acting on this point, rather it might be acting on this point with some eccentricities, which will be giving you some Ex and Ey values. Therefore we cannot proceed accordingly for the concentric columns. The formula will not be valid there, and therefore there are two methods, and from which we will be using the reciprocal method. You might have learned about this, the reciprocal methods for designing eccentric columns. So that method will be applying here, and for that there are some different charts are there which we'll be learning one by one. First of all, for concentric column, if I say first of all you will have to choose one column dimension. So you are assuming column dimension, column of say 15 inch 15 inch. Okay, so 15 inch 15 inch is the initial column direction which we will be using. So initially you will have to define some column dimensions, and I will be fixing you these things as like you will have to assume one dimension for particularly one dimension for all the edge columns. One corner columns will be corner columns of a particular size, then edge columns of another particular size, and middle columns another particular size. So three types of fixed dimensions we'll be using for corner, edge, and middle columns. So say for example you will be assuming 12 into 12 inch for corner columns. For edge columns you might be using 15 into 12 inch, and for the middle columns you might be using 15 into 15 inch according to the necessity. This is just from my suggestions, but not necessarily you'll have to take these values. You can increase the values of dimension as well. So for initial trial you can take any assumed values. So not necessarily this will be always satisfying the conditions, not necessarily, but you will have to assume one initial dimensions. If it is not sufficient, then you might have to change the dimension as well finally. So first of all, if we assume, say let's for example we are assuming 15 inch into 15 inch for any particular column, and say we are just assuming this for the edge column C1 as well. Okay, so all the corner columns. So for edge columns you might be, say we have obtained this value, like say we have obtained the axial force is 300, bending moment m1x is 25 and m1y is 55 we have obtained. So using these values we'll have to check whether this will satisfy or this will satisfy the loading conditions or not, and for that we'll have to again define the column reinforcement pattern as well. So say for example this is the 15 into 15 15 inch into 15 inch column. So for where we'll have to again obviously provide some ties, lateral ties we'll have to provide as well. So say for example this is the lateral tie conditions, and in which we'll be providing the reinforcements as in this particular pattern. This pattern is, again remember, this pattern is very much important here, and for this we'll be again using some other ties. So this type of ties we'll be using again, and you will be using ties like this one as well. So why we have given this pattern, you know that as this is 15 inch. So if it is the intermediate two columns, two reinforcements is greater than 6 inch, then you must provide intermediate ties as well to bind all the reinforcement, to keep all the reinforcement within combined together. So you must provide this type of ties intermediate as well. So there are some guidelines as well, so I'm not going to discuss these things. You will be designing accordingly as the guideline says. Whatever you will have to provide, you will be providing like that. So not necessary I'll have to discuss this. This is not necessary in our for this concern. Okay, so what we'll be focusing here, that is the total dimensions will be focusing here. Okay, we'll be focusing on the total dimension. So if it is 15 into 15, so it will be like this, 15 by 15. And obviously for columns we use what, 2.5 inch covers. So 2.5 inch covers in each dimensions. So 2.5 inch, 2.5 inch. So in this pattern we'll be providing the you know what, we'll be providing all the reinforcement, and therefore the distance between these two extreme reinforcements will be in this particular case 2.5 inch will be deducted, so 10 inch, and in between these two the distance will be 10 inch as well. So these things are required just because of whenever we'll be applying for eccentric column, the reciprocal method will be needing these dimensions. So this pattern will be following for our method, this example. So for your particular case, whichever the pattern you will be using, you must mention it first. So for trial we are giving this column size. So from there, if you calculate the AG, the gross area will be 15 multiplied by 15, that will be 225 inches square. And for column, as you know that the reinforcement ratio, the allowable reinforcement ratio is 0.01 to 0.08. The maximum up to 0.08 we can go, but in general we do not go. We prefer to keep it within 2.5%, or better not to exceed 4% as well. So there are some guidelines, as you know. I'm not going to mention these things. So maximum reinforcement ratio which can be provided, that is 0.08, and the minimum 0.01 is there. So within this range we can use any values, but keep remembering that it should not be exceeding 0.08, the reinforcement ratio. So if we want to know the actual reinforcement area which we can provide according to this row, we can calculate these things. Say for example AS, if you use rho equals to 0.01, then AS, as you know that the rho BD, so 0.01 multiplied by B, that is in this case BD, these two things all are similar in case of column, although we say rho BD in case of beam, but in this case D instead of D you will be using H. For column, the area, the gross area, rho multiplied by the gross area, that will be the area, and multiplied by rho, which will be giving you the AS value. And from this calculation you will be getting this 2.25 inch square. So minimum 2.25 inch square reinforcement must be provided within this column if the dimension is 15 inch by 15 inch. And if we use the maximum reinforcement ratio, which is 0.08, let's see how much amount of the reinforcement we can provide. 0.08 multiplied by 15 multiplied by 15, which will be giving you 18 inches square. So the maximum amount of AS steel which can be provided within this column, that is 18 inches square. So in our trial calculation, say and what will be the, for if it is the concentric column, there is no eccentricity within this column, then what will be the maximum strength, how we can calculate this thing. The formula, this is very well known to us, and we are again writing the equation for your convenience, the maximum capacity of the column will be according to the formula, that is 0.85 multiplied by 5. Then within this 0.85, FC prime AG minus AST, that is the capacity of concrete, the strength provided by the concrete, and the strength provided by the steel. Combination of these two will be multiplied by this, reduced up to a certain amount of capacity to get the original capacity and the final capacity of the moment. This value, this formula, we can use for concentric columns. So if you use AS equals to 4 inches square, for example, so in this case, if you use 4 inches square, that is, say if we are using 4 number 9 bars in the column in 4 corners, in case we know that even in column number 9 bars are not sufficient, we do not use generally, but number 9 bars, okay, you can provide. If we provide number 9 bars, for example, in the column 4 number 9 bar, then we'll be getting 4 inches square of AS. Although the guideline make you flexible to take 2.25 inches square, but in practical purpose you cannot go beyond the 4 inches square. You can see from this that if the minimum 4 number 9 bars are used in 4 corners of this column, you will be getting the 4 inches square of AS here. So that's why if you use this one, the phi PN, the maximum value according to the above equation, you might be getting the value, if you calculate this value, what you will be getting if you calculate this thing. Another thing it worth mentioning that this particular formula is for what? Tight columns, tight and rectangular columns. Okay, the rectangular columns will be using this formula, and for that particular tight column we'll be using 0.65. Phi equals to 0.65 for tight columns, as you know. So there are other types of columns as well, as you can say the circular types of column, this pattern, these columns, as you all know, but we are not using this here. For that particular types of column, there will be different equations with having different values of different factors as well, so which we are not using here. So whatever it is, the phi PN, if we use, say for example this particular case, the column will be changing the strength amount. I'm changing this thing, the FC prime value will be changing here up, say 4000 psi we'll be using, and Fy will be using here for 60,000 psi. Although in beams we have used different values, but for columns, say that we will be using this value, which will be making our calculation simplified, but not necessary for your case. For your case, the strength might have been given to you, that particular strength which will be using for your particular case. However, so let's calculate the value of phi PN max. For if we use 4 number 9 bars, you will be obtaining the value if you use this as 4 and this as 60 and all the KSI value. If you put it down, you will be directly getting the value in kip, and that will be 457, so 547.74 kips. Okay, so these values we are getting from, if it is concentric column, then it will be able to withstand this amount of this amount of load, as you can see from here. And if we use, say if you use AS equals to 8 inches square, as it is what we'll be using for our particular cases at 1, 2, 3, 4, 5, 6, 7, 8 number of bars, and if we say all these bars are 8 number 9 bars for our case in this particular, so we are using 8 number 9 bars. In that case we are obtaining 8 inches square of area, and obviously we can use this just because this is our range within 2.25 inches square up to 18 inches square we can use. So maybe if you use 8 inches square, then you will be getting, say for example, the phi PN max if you calculate from this particular value, you'll be obtaining the calculation in this particular equation. If you put the AST value, the steel area, then you will be getting the value as 672.83 kips, similar to this one. So it will be able to withstand this amount of load if the column is concentric column, that is if the axial load is acting on the center of the column. Unless this is acting on this one, if it is eccentric column and there is an eccentricity because due to moments, then the capacity will be reduced, and the reduced capacity that we will be calculating using reciprocal method. So for initial trial, we'll be using this 8 bars within 15 inch into 15 inch column. So for your case, you will be, as I have said, you will be taking 3 types of columns, and for 3 types of columns you will be defining 3 types of dimensions according to your convenience. And obviously you have FC prime and FY, then you will be defining a particular pattern of reinforcement. You can provide as I have provided, or you can provide other patterns as well, as say for example, you might be providing the reinforcement in only 1 layer, 2 layers. This type of reinforcement pattern you can also provide as well. So based on the pattern, you will have different types of interaction diagrams, and from those interaction diagrams you will have to calculate the reduced capacity of the column according to the reciprocal method, which we'll be going to discuss here now. So what we have seen, if this number of bars are used, so for example, if 9 number of bars are used, then if it is a concentric column, then you will obtain the capacity of the column is 672.83 kips, so which is well above the value 300, as we have seen here. We don't need this amount of reinforcement to withstand that one, but still, as we know that the capacity will be reduced due to eccentricity, that's why we'll be calculating using reciprocal method now. So let's use reciprocal method first. So first of all, we'll be writing that compressive force on column. So for C1 we are calculating here, so 300 kips. Okay, 300 kips. Now we'll be also writing the M1X value, which is 25 kip feet, and also the M1Y value, which is 55 kip feet. So from these two values we know what is moment M1X. M1X is nothing but the eccentricity, the PU multiplied by eccentricity in Y direction, and M1Y is nothing but the load, that is the axial force multiplied by the eccentricity in X direction. So that is nothing but, if we discuss it about here again, so if in Y direction, say this, if this is M1X, the load is acting over here, say the PU load is acting on this point, and for this value, this dimension is EY. So this load PU multiplied by this eccentricity EY in this point will give you this M1X. So while M1X, you will be multiplying PU with EY, and when M1Y, you will be multiplying PU with EX, just because this direction, the eccentricity, if it is there, then this is EX. Okay, so these two are the formulas for us, and from there we need to calculate the eccentricity. So EY you can calculate as you have M1X divided by PU, M1X which is 25 and PU that is 300, and from there we'll be able to calculate the value, if we multiply this with 12 as it is in feet, then you will get the EY value in inch, which will be getting as 1 inch. And also for EX, if you calculate this thing like this, 55 multiplied by 12 divided by 300, which will give you 2.2 inch. So EX and EY 2 we have already obtained from this calculation. Now we will be applying the reciprocal method. As you know, the reciprocal method, for applying this reciprocal method, we need to know some factors, which is gamma, and we need to calculate E by H. We need to know the rho. Using these factors, we will be calculating the capacity, the reduced capacity, by calculating the capacity in different directions, x and y directions. So for reciprocal method, we are just using reciprocal method here. We are using reciprocal method. First of all, we will be getting it for about y-axis first. So about y-axis, whenever we are using y-axis, what is the value of gamma? Gamma is nothing but the ratio of this one. You see, if this is, as you can see, if this is the column, if this is the y-axis and this is the x-axis, and the column, you must have these values as well. So this type of column in our case, as we know. So if about y-axis, you will be taking this value gamma as this one and this one. So if it is A and if it is B, then gamma is nothing but A by B. So in our case, you know that this is, we have calculated 10 inch after deducing 2.5 inch in each side, and this is 15 inch. So in our case, gamma will be 10 by 15. And about y-axis, whenever we are calculating, then gamma you will be obtaining as 0.667. Okay, so keep remembering that this is nothing but although we have said A by B, in your textbook you can see that in each cases, whenever along y-axis you are calculating, you will be taking which one? When it is towards y-axis, you have seen, you have to keep remember this thing, that whenever you are concerned with a particular axis, then this gamma will be the ratio of the distance along with respect to this axis, whatever the you know what the depth is. If according to y-axis the depth is in this direction, x direction, so the total width of the, that is we say depth of the column, say h, this h will be our constant. So this 15, that is h, and the reduced distance, the intermediate distance of the two extreme reinforcement along this depth, that is distance will be 10 inch, that will be our constant. So whenever we are focusing on x-axis, then we will be taking the values so we'll be taking the values whenever in this direction, then we'll be taking depth in this direction, just because if you are parallel to x-axis, then you will take this one and this one. The ratio of these two will be taken as gamma in case of x-axis. So y, as we are using about y-axis, so that's why we'll be taking this one. Although this is a symmetric column, as we know that we have taken the square column, so the gamma for both of these two cases will be the similar, that is 0.667, but not necessarily in your case the both directions gamma will give you the same value. So that's why I have explained this method how to calculate this gamma for different axes. Whenever in y-axis, this y-axis you'll be taking these two ratios, and whenever x-axis you'll be taking these two ratios. Okay, these two ratio of these two. Now we'll be going for calculate e by x. Whenever you are in about y-axis, keep remembering this fact that you will be taking the ratio of ex divided by h. H, what is h? Whenever you are concerned with y-axis, that h is this one, as I have explained, and whenever you are concerned with x-axis, the h will be that one, this one. Okay, so ex by h, that will be equals to 2.2 divided by 15, and that will give you a value of 0.147, which we can write is approximately equals to 0.15, and rho is equals to, say will be using rho equals to 0.04 for our convenience. Okay, also in your case, so in our case, say we are using reinforcement ratio is equals to 0.04. We are not going to provide a reinforcement ratio beyond 0.04, so not necessary, although if we use 8 number of 9 bars, which will be giving you like 0.035 something reinforcement ratio, but just ignore this thing. We are taking rounded value for our convenience in this case, but you will be taking the rho value according to your calculation, your particular section rho, which will be governing the reinforcement which you will be providing. According to that, the rho you will be calculating just the area as you are providing divided by BH. This will be your reinforcement ratio. So for our convenience, we are just assuming we have taken rho equals to 0.04. Okay, so now what do we need? We have already three values, this one E by H, that one 0.667, and this one. Using these three, you will have to calculate the capacity along about y-axis, so for which we will be needing a graph. So for that, let's focus on the graph. This is the graph, very well-known graph. So there are different graphs, as you can see. This is the initial graph. So you will have to fix the pattern, which pattern of columns we have taken. So this is our concern graph. So see here, you can see fc prime 4 ksi, fy 60 ksi, and gamma equals to 0.6. Although our gamma, as you can see, we have obtained our gamma as what we have obtained. So we have obtained 0.667, as you can see. So as you can see that we have obtained 0.667. If you see, we have obtained 0.667 in our case, but here you can see the gamma is equals to 0.6. So also we have the similar pattern, fc prime equals to 4 ksi, fy equals to 60 ksi, and gamma equals to 0.7, but we don't have 0.667. So what we'll have to do, we'll have to apply the unitary method or the interpolation, whatever you say. So we might use that particular formula of interpolation or unitary method to calculate what will be the value of 0.667, gamma equals to 0.667, as we have 0.6 and 0.7. So in between that 0.667, we'll have to calculate with using these two graphs, and also keep focusing on the pattern. So we are using this pattern of column, as you can see here, and also you can see in this particular figure that this is the pattern we are using. Okay, but not the pattern. The similar value might give you another pattern which we are not using, that is you can see this say this particular value, this particular graph, fc prime is equals to 4 and fy equals to 60 ksi, gamma equals to 0.6. But this pattern is not our concern, as I have said that we have provided reinforcement in all 4 directions, not only two directions like this. Also we have provided throughout the column. That's why we cannot use this graph for our concern. So there are different graphs available already in your textbook, but you might ask me the question, what will happen if we don't get the value? Say for example, if you have strength, different type of strength, fc prime is not equals to 4 and fy is not equals to 60 and different combination. In that case, I will say you must have learned how to draw the interaction diagram. In that case, you will have to draw interaction diagram of your own, and then from that particular graph you will be obtaining the values, our concerned values in that case. So that is your responsibility how to draw this if you have different type of string combinations. And in that case, and I know that different online sources are there for where automatically interaction diagram will be generated. So you can also search for that. So ready-made graphs will be generated for fc prime and fy and particular gamma value, and from there you can easily obtain your concerned values from that particular graph if you don't find it in your textbooks already given graphs. Okay, so let's use as for our convenience, we have already these 2 patterns, the graphs already given there. We will be using these 2 graphs, this gamma equals to 0.6 and gamma equals to 0.7 to calculate our values. Let's see how to calculate. So we go back to our calculation. Let's go back to our calculations. So in this case, we will be using graph A5 and A6. These 2 graphs we will be using, and we will be getting P and Y naught, as we are concerned with about y-axis, divided by fc prime ag, and we'll be getting the average value using average means interpolated value, interpolated using unitary method, whatever you say. So that will be, say, as we have gamma equals to 0.6 and gamma equals to 0.7. So if we multiply this gamma equals to 0.6 value with 2 and this gamma equals to 0.7 value with 3, and this value with 1 and this value with 2, and divide the total value with 3, then you will be obtaining value for 0.667. Can you understand what I'm saying? This is if say 0.6, if it is weighted up to 1, 0.6, not 0.6 actually, the value of this one for gamma equals to 0.6 multiplied by 1, and gamma 0.7, the value of this one for gamma equals to 0.7 multiplied by 2, and if we divide it by 3, then you will be getting the value which is concerned with gamma equals to 0.667. So from your basic common sense you can apply this knowledge. Also, what you can do, you can this is the fact what we have said, but you can also use the interpolation method, that for 0.6 gamma we have obtained this value, for gamma equals to 0.7 we have obtained this value. So using these 2 values, so what will be the value for 0.667? So that method you can also apply. So I am just using this method. We can use any other methods for interpolation to obtain the value for 0.667. That is up to you. Or if you can generate gamma equals to 0.667 and automatically generate all the strings graphs using any online sources, then you are also welcome. Then in that case you can directly obtain the value from that particular graph which we had drawn for this particular 0.15 ex by h, and for gamma equals to 0.6 and fc prime fy all are there. Although this value will be obtaining, you will be using within the graph. So our main concern will be if you can draw the 0.667 gamma value, generate the interaction diagram. That will be very helpful for you as well. If not, then please apply the intermediate values of the known values to obtain the original value using interpolation as I have shown here. So let's see, for 0.6 we'll be using, let's go to the graph. Let's go to the graph. From this graph, in this particular direction, we don't have to concern about this one. Now we'll be concerning about this one, that is Pn by fc prime ag. And as we are concerned with y direction, that is will be getting this value for y direction, about y-axis. So for y-axis, we know we have e by h value of what? If you can remember, e by h value is 0.15, as you can see. So for e by h 15, as you can see here, 0.1 and 0.2 is there, and there are different marks upon there. If you extend this line, this particular line, that is 0.15 line, and connect it with the 0 point there, this will automatically intersect. As you can see, all the lines are there, parallel lines. These lines are representing rho g, that is the reinforcement ratio, and our reinforcement ratio, if we can recall the value of reinforcement ratio, is 0.04 we are using here. So for 0.04 line is this one, and the extended line of e by h equals to 1.15 will be intersecting this 0.04 in a particular point, and that particular point you will be directly going to this one to get the value. Say for example, this 0.15 line and 0.04 rho point has intersected together within this point, which will be giving you, say for example, this point, and we are taking the value. For example, we have taken, say for example, this is 0.92, and as I have said, we'll be multiplying it with 1 plus. Now we'll be going for the another graph, this another graph where gamma is equals to 0.7, and where gamma is equals to 0.7, you will be again searching for e by h equals to 0.15, that is this line. If you extend this line, and rho equals to 0.04 already, so this line will be intersecting point. If it is connected to 0 point, this will be automatically intersecting 0.4 in any particular point. Say for example, this will be intersecting this in this point, from which if you go directly in the left side, you will get the value. Say for example, this point, you will be getting this value as, say for example, we are treating this value as 0.96, and this will be multiplied by 2 as I have said, and it will be divided by 3. Not necessary you will have to apply this method. You differently use, you obtain for 0.6 this value, 0.7 this value, and from that 0.667 what will be the value, you can also calculate. It will be giving the same value as I have applied this formula. You will be getting the similar value. You can try it of your own, and from there we have obtained the value as 0.947, and from this we can calculate the P and Y nominal strength about y-axis, which will be 0.947 multiplied by fc prime multiplied by ag gross area. So fc prime already know with that this is 4 ksi, and ag, the gross area, we already know that this is 15 into multiplied by 15. This will automatically give you the value, which will be 852 gives approximately, say. So 852, this is the capacity in y direction about y-axis whenever we are concerned with y-axis. And also you can calculate the nominal strength for concentric column. So when it is concentric column, then E by H literally is equals to 0, that as there is no eccentricity. So E by H equals to 0 from the similar graph in both of these two graphs. If you go for this graph of point for both of these the two graphs, if we go for 0.7, this is 0.7, and if you go for 0.6, whatever it is, for both graphs, E by H equals to 0 is this line itself, this line, and for 0.7 this line as well. So the similar line, whatever the line is, if you go for E by H equals to 0, this line is automatically intersecting with 0.04. You see where 0.04 is directly intersecting the point in this point. For example, if we are treating this value as 1.41, also if you go for 0.7, you will see the similar scenario here. 0.04 is intersecting this point. So for if E by H is 0, whatever the gamma is, it doesn't matter, you will get that always. If Fc prime and Fy is fixed, then P naught, you can easily calculate the P naught by Fc prime Ag. The value is 1.41, and from where you can calculate that P naught value is equals to 1.41 multiplied by 4 multiplied by 225, that is 15 multiplied by 15, and from there we can obtain the value. The nominal capacity of the column is this one. And remember one thing, in this case the calculation, if we just say this again, the P naught by Fc prime Ag, you have shown that 1.41 as we have seen from the graph. So and 1.41 will be there, and P naught Fc prime and Ag will be multiplied by this one, and to obtain 1269. And if you focus in this, that in the this value we don't have any reduction factor. We have seen the formula there. There was a formula 0.85 multiplied by 5, and there within this value there was a particular value. So this actually represents the value within this one, not beyond that. This value is actually representing this one. So if you want to calculate for concentric column this total value, so you will have to multiply it with this 0.85 multiplied by 5, that is 0.65. So if you multiply this with that one, you will be obtaining, say, let's calculate this one, 1269 multiplied by 0.85 multiplied by 0.65, you will be obtaining the value is almost equals to 701 approximately. So this is the concentric column capacity if you are using rho equals to 0.04. That is what we have calculated using the basic equation, that is this particular values, like this one. In this case we have used 8 inches square. 8 inches square means rho equals to 0.0356, something like that, and for that rho for concentric column we have obtained the value as 672. And if we had used rho equals to 0.04 in that particular equation, this equation, and that is the AS governing this rho, then you might have obtained this value as 701 gives. So that is the significance, approximately use 701 if you have used this one instead of this one, that is 8 inches square, 8 number 9 bars. Then we'll be getting this value, so which is also we are getting from this graph as well. So for concentric, so this value is without this one, that is all the reduction factors, the 5 factors, the 0.85 factors, as you can see from the graph. We have directly used these values. We haven't cut the values in this portion, and neither we have multiply this value with the 5 values. Other than that, we'll be getting the similar values. Okay, so that is not our concern. This p naught that we'll have to use. That's why we are again calculating and showing these values like this. So y-axis, about y-axis is completed by this time. Now we will be focusing for about x-axis. So let's start about x-axis. So about x-axis, now we'll be using about x-axis. Now we'll be using about x-axis. So now we'll be using about x-axis. We have said that maybe you haven't seen just because of graph. I'm again mentioning that we have obtained, if we haven't used this 0.85 and 5 factor, you will be getting this 1269 keeps. But if you use this value, you will be calculating, if you multiply this value, that is phi equals to 0.65 and 0.85 multiplied by 1269, you will be getting this 701 keeps, and that is whenever you will be using rho equals to 0.04. And the similar value you might be obtaining, as I have shown here earlier, that in this equation, this particular equation, you can also obtain the similar value. So the phi mn max will be 701 in your case, 701 keeps, if you have used the as in such a manner that the rho would have been equals to 0.04. We have used in this particular case 8 inch square, that is 8 number parts, which is equivalent to rho equals to 0.0356. How you have obtained rho equals to as by bh. So using this formula, you can find out this rho, that is 0.0356, and corresponding as 8 inch square, we have obtained the strength of the column, concentric column, that is 672.83 kips. But if we have used, if we had used this rho equals to 0.04 and corresponding as will be something, that particular as would have given you this particular value as 701 keeps as concentric values, which is also similar to the value which we'll have obtained from the graphs and multiplying that with 0.85 into 0.65. So we haven't got this just because this value is not the final capacity, just because if we again focus on the graph, that in the graph you see we haven't focused on this just because we haven't reduced the values in this particular cutting point, rather we have taken this one. So to reduce this value, you will have to multiply 0.85 and multiply 0.65 as well after that to get the original value, which is similar to the equation is as we have represented earlier. However, now we are going back to our calculation. We are starting the about x-axis calculation, which will be also similar. The rho will, in this case as well, as we have said that whenever we are about x-axis, so about x-axis we will be getting this ratio. So this is 10 inch and this is 15 inch. So again 10 by 15, which will be equals to 0.667. And in this case we'll be using EY by H, and H, you know, this is H whenever we are concerning about x-axis. While you are in y-axis, the H was this one. So this H, all just because this is a square column, that's why no change in this. But if it were a rectangular column where different dimensions in different directions are there, then you will be getting different H for different axes. So EY is, you know, that 1 inch you have calculated before, and H is 15. So from there we can calculate this value as 0.06667. So in this case we have also found the value as 0.0667. 1 by 15 is 0.0667 and gamma is 0.667. And what about row? Row is the similar thing in both directions, just because the row is a scalar dimension which is not dependent upon any direction. The total reinforcement area divided by the total gross area, that will be giving you the row value, and that is 0.4. As we have used for y-axis, the x-axis will be similar. Now we'll be calculating using these two the capacity in x-axis, that is Pnxo divided by Fc prime Ag. You will be getting it from the similar. We'll be again interpolating this to get rho equals to 0.667. as we don't have directly 0.667 graph, we have 0.6 and 0.7. so from these two graphs again we'll be calculating this thing. So let's see what we get from two different graphs. From 0.6 graph we have now the E by H equals to 0.667. so 0.667, you will have to assume a line from 0 to 0.1. say a line will be there 0.0667. E by H equals to 0.0667. there will be a line within say in this region. Approximate line we'll have to assume, and then we also have rho equals to 0.4. The point where it will be intersecting together, we'll be getting, say, we'll be getting from here one value, will be getting one value. So one value for 0.067, which will be intersecting with 0.04, will be getting a value here. That value will be taking as a value, say the value will be, if we start from 0.067, 0.067 will be a line starting from here, say for example, which will be intersecting this 0.4 value in this portion. Say 1.2 we have obtained, say for example 1.2 we have obtained, which will be multiplied by 1, and sorry, which will be multiplied by 2, and the value will be, that's why we have written here, as you can see, 1.2 multiplied by 2, and the point for 0.667 0.7 we get another value. Let's see here, 0.7. For 0.7 you will be getting the value 0.67 line will be like similar in this point, and this will be intersecting this in, say for example, this point, which will be say 1.14 for example. So it will be intersecting here in 1.14 or 15. say if we use 1.15 multiplied by 1, we are taking 1.15. so 1.15 multiplied by 1 we are using, divided by 3, or you can also use, this is 4.6, this is 4.7, so what will be 1.0667. so from this calculation you will be obtaining the value of load axial force in x direction, which will be say almost equals to 1.18, we can say. So okay, use 1.18. so what will be P and x naught? That will be 1.18 multiplied by Fc prime, that will be 4, and Ag is 225, which will be giving you, if you calculate 1.18 multiplied by 4 multiplied by 225, which will be giving you 1062 kips. 1062 kips. This is the value P and x naught. Also you can calculate the value for concentric column again, which will be giving you all the similar value as we have found for the previous about y-axis. So let's go to the graph again. Again we'll be getting the same value. Say whether it is 0.7 or 0.6 doesn't matter. E by h will be 0 in this case, and for 0.4 you'll be getting 1.41 in both of these the two cases, gamma equals to 0.6 or gamma equals to 0.7, it doesn't matter. So you'll be getting what? 1.41. So 1.41 will be getting, and from there P naught will be automatically getting the same value as we have obtained in the last calculation, that is 1269. So this one is very much important for us. This P naught, whatever we take from this one or that one, it doesn't matter. 1269, that is PU. Now we will be calculating the reduced capacity. The reduced capacity according to the reciprocal method. If we substitute the values in reciprocal method, the original nominal capacity of the column is equals to 1 by P n x naught plus 1 by P n y naught minus 1 by P naught. 1 by P n x naught we have calculated just now, 1 by 1062 plus P n y naught about y-axis we have calculated as 852, as you can see here. So 852 you will be using, and P naught 1269 as it is. From there you can calculate the Pn value, which is equals to 753.4 kips, and this is the value of the nominal capacity of the column when it is with having eccentricities of ax and ey as it is, that is the axial load with the moment, which will be reducing the moment capacity up to this one. And if we factorize this thing to obtain the final value, that is Pu will be nothing but equals to 5Pn, that is 0.65 as tight column, that is 753.4 will be multiplied with this one to obtain the final value, which will give you 489.7 kips. Can you imagine this thing? This is the reduced capacity of the column, whereas if it were the concentrated column, then the nominal capacity would have been 701. 70 kip it might take if it is concentrated without any eccentricity or moment, bending moments, but whenever it has bending moments acting over there, then the reduced capacity of this particular moment is this one. Up to this axial load it can resist. And as we have seen that our load, we have obtained the axial force was 300 kips. So as it is well below this one, so the moment the column capacity of the axial force is well above the axial force which it is experiencing, we have found from the combination the maximum axial force of the column. So we can say that our designed column, that is this column is satisfied, it is satisfying this all the necessities. So we can finalize this as the design. And remember that the exception is we haven't used this 8 number 9 bars. This 8 number 9 bars would have given the rho equals to 0.0356, but we have used rho equals to 0.04. So based on 0.4 we'll have to provide the reinforcement in such amount so that the rho will be equals to 0.04, or it might be slightly greater than that, we wouldn't mind, but not 8 number 9 bars we are giving here. as we have shown there. So then the column will be satisfying all the necessities. Or you can also check with row equals to 0.0356. If you are stick to the 8 number 9 bars, in that case what you will have to do, you have to only go to the graph. If we go back to the graph, you will have to only take the instead of 0.04, you will be assuming another line in between 0.04 and 0.035, a line which will be representing 0.0356 is that particular line which will be intersecting with this EH. That values you will have to take. That is the only difference, and all other things being the same. So I hope you have understood what you have to do with these things. So if you find all these columns, so for edge columns, corner columns, so if corner columns are there, as we have seen, all corner columns C1, C4, this one and this one, so you will be checking in similar way whether that particular capacity, this value, this final value, whether this final value according to your provided reinforcement, whether this is greater than the values of C1, C4, all corner columns only. If it is if the capacity is well above all these 4 ones, then you can say that your design is okay. So you can fix this particular dimension for all corner columns, and I will be obviously recommending you to take whatever you take, the edge, all the corner columns will be having the similar amount of reinforcement and similar dimensions, and all edge columns similarly you will be fixing the edge column and showing that all the edge columns are satisfying the needs, the capacity of that particular edge column according to your reinforcement provided by you, and all the middle columns accordingly. So these 3 types of column, you'll have to choose 3 column types and finally show that all these are satisfying this. That is your task for while designing column. And another thing I must mention, that how you'll have to provide the tie. There are directions for providing ties. So if you use number 3 ties, tie bar. If number 3 tie bars are used, so there are some guidelines, as you know, for which number of bars you can use number 3 tie bars and for which you will have to use number 4 tie bars. I don't want to mention all that things here again, but you know these things, and if not, please focus on your textbook and recall this in your mind so that you can use all those tie bars and number of tie bars properly according to the number of reinforcement, main reinforcement provided in the column. So if number 3 tie bars are used, then what will be the spacing? The spacing, according to the code, as you know, that the guideline says that it should be the smallest of 3. Which 3? First one is the 48 dB. 48 dB. dB is the bar diameter of what? The tie bar. And sorry, this will be, sorry, this is not, this will be 16 of bar diameter. Bar diameter means what? This 9 number of bars, the maximum number of bars used. If you use multiple number different number of bars within main reinforcement, the maximum number of bar dia will be used here, as you know. If then 48 diameter of tie bar, and finally it will be the minimum dimension of column. So these things, smallest of these 3 will be taken. So 16 bar diameter, 9 bar dia if it is used, the number 9 bar dia is 1.128. and if we use tie bar number 3 bars, then bar diameter is 0.375, and minimum dimension of the column, as it is square column, both direction it is 15 inch. If it were a rectangular column, that the minimum dimension we will be using there. So from these three, whichever the least one, from this one you get 18 inch, also this 18 inch, so this 15 inch will be governing here. So the tie bar will be providing number 3 tie bars at the rate 15 inch center to center. That will be your design. So that's how you will have to design the columns. All the columns, 3 types of columns you will have to design, and there are some guidelines you will have to show that if this is the tie bars as you will have to provide, you will have to show the column reinforcement in this type of view. This is the column. So if this is the column, the total column, you will have to draw the main reinforcement like this. Okay, then you will have to provide the tie bars like this, the tie bar spacing, as you know. And as there are guidelines, you know, I'm not mentioning in details what are the guidelines, as you know that whenever this is close to joints up to some distance, you need to close the spacings as well according to the guideline, according to the code. And in all other cases you will be giving the tie bars accordingly as it is at the rate 15 inch center to center. So from that's how you will have to show all this column. This is the longitudinal section, and the transverse section you will be cutting the column in different portions. And one thing you should remember, that the value we have taken, which value? This value we have taken, but what about this one, this one, this one? So therefore you must need to cut off the columns. That is, whenever we are going above and above, for example, in general, if we go above up to some distance, say this is first story, second story, then you might not be requiring the similar amount of reinforcement as we have used. If you have used 8 number 9 bars after 3 or 4 story, you will not be needing 8 number 9 bars. You might you can cut these two or these two and keep only 4 number 9 bars. That is possible. So that will be also requiring the moment, the amount of moment values, the values of moment you will be taking. Although I have said to keep safe distance, to take the maximum value of moments, I have said in whichever portion this is, I have said to take this. Although you may take the maximum within this portion, that might have been enough for you, but still we have said to take the maximum value, although it is not required. But again, whenever you will be satisfying the conditions, you will have to show that, say after 2 or 3 stories, you will be considering this particular axial force, the maximum axial force in for all the corner columns. You will be comparing with this 3-storied or 4 number of stories equals to 4, the axial force and the maximum moment. You will be again giving the total trial again to see whether you can adjust this, cut off this 4 to get this number 9 bars is satisfying the load or not, the capacity, whether it is governing this axial force or not. If you see that okay, it is satisfying, what you will have to do while designing this longitudinal column, say this is the bottom story, second story, in third story, whenever you have gone, then you will be just removing this one you will be cutting this thing. But although there are some guidelines, you will have to also show these things here. In practical purpose, we cannot cut this close to the joints. After it exceeds joint, then you can cut this one. You cannot cut just after joint. And there are some guidelines. If you cut this particular reinforcement over there after exceeding a sufficient distance from this joint, then you can cut this thing. So if you cut, you will have to maintain a aspect ratio, like if this is the pattern, now after going in this portion, you will be cutting in symmetric pattern. Say we will be cutting these two, and not 4 at a time, just 2 at a time. Say you have cut these 2 at a time, then after a sufficient distance, or going to another story, you will be cutting these 2, and finally this 4 will be continuing further. So not at a time you can cut all the 4 at a time. Keeping symmetry, you just cut off 2. In another story, after going sufficient distance from the joint, you cut off these 2. That's how you can proceed. And to maintain, this is the practical design aspect which you should maintain, you will have to show in longitudinal section. And from there, what you will do, you will have to show, if I say that the minimum thing, this is the cutoff you will have to show. So while showing in section, this is the longitudinal section. When transverse section, you will take a section from this one, usual section as designed. Another section you will be taking close to the joint to show this spacing in the transverse section. Then after cutoff, you will be taking another section in the middle. Then after second cutoff, you will be taking another section at the middle. So this section, as 2 reinforcements have cut off, the section will be removing these 2. Can you understand? The section will be like this one at this particular portion. And when we will be going to this portion, when the remaining 2 will be cut off, the transverse section you will be showing like these 2 will be, sorry, so these 2 will be deducted from that. Then this section will be only remaining. And obviously don't forget to show these tie bars as well. And this tie bars, you will show number 3 tie bars at 15 center. So center whenever it is in the middle section. When it is close to the joint, you will be showing number 3 tie bars at the red with the reduced spacing according to the guideline and according to the code. And that's how you'll have to show all the section. So this is one section which is for corner columns. So 3 types of column. For edge columns, you'll have to do all the similar thing. For middle columns, you'll have to provide all the similar things as well. And remember again one thing, that you will not be taking for 4 of the columns, say from this from all these corner columns, you will not be taking only the maximum. Rather, you will perform the same calculation for all of the 4, as we don't know that whether this moment can reduce the capacity up to which extent. That's why even if you have got the maximum axial force for similar corner columns or similar edge columns, you will not be only focusing and restricting your calculation for particularly that column only. Rather, you will have to perform the same calculations for all of the columns. And finally, the finally governed section, the trial section, just because you will not have to design the section again and again, just you will have to update if necessary. Other than that, you will have to check all the columns that will be satisfying the criteria. That's how you will have to proceed and show the designs, the columns in your calculation, in your assignments. So I hope I have completed all of these things. I hope you have enjoyed. If you have any further queries, you can ask me, then I will try to give answers. And obviously another thing I forgot to mention, that you will have to keep remembering that according to our guideline, the code says that in particular cases where seismic designs, seismic provisions, seismic provisions if followed, then according to the seismic provisions, you will have to also provide the column spacings, tie spacing. You will have to maintain those aspects as well. If you don't know about this, you can go for the your textbook. Let's see whether I can show you or not. In your book, I can direct you to read some of the portion. You might have read these things earlier. If you haven't, then I will suggest you to focus on this once again. So all the seismic provisions are shown. So if you are designing IMRF, intermediate moment frames, then these guidelines you will have to follow. All these things, just follow these articles. I think you will be getting some directions. So how to design seismic columns, seismic frames, all these guidelines you will be getting from this particular article, I think. And if additional things are needed, you can search for that. So maintaining all these aspects, you will have to draw the designs, the section, the longitudinal and transverse section accordingly. Okay, thank you for being present in this class, and hopefully you will be able to submit all these things successfully. Okay, so thank you everyone.